Welcome back to part 2 of lecture 8. So we just finished defining permutations and combinations, and we did some simple examples to demonstrate how they work. We just saw this last one here. What we're going to do now is we're going to move on and do some more complicated examples and ones where it's not clear to us at the beginning what technique to use. So the first one we'll do is number 31 on page 65 of the textbook. And in this problem, a radio station plays one Beethoven symphony and then one Mozart piano concerto. And since there's 9 Beethoven and 27 Mozarts, how many ways can you do this? Well, I guess the first thing to think about here is, does order matter? Because that's often determines how we approach this problem. In this case, I would say it does, because it matters which thing you play first. So order matters here. And that suggests that we might use the product rule. And in fact, once we've figured that out, there's not much more to say than the answer, because the product rule simply says it's the number of ways you can choose the first component of the event, which is Beethoven. So there's 9 choices there, multiplied by the number of ways you can choose the second thing, which is 27 Mozarts. So that's the answer, 9 times 27, or 243. There's 243 different ways you could play that. Part B of this question is along similar lines. Suppose that every night the radio station will play one Beethoven followed by one Mozart followed by one Schubert, and that there are 15 Schuberts that they can choose. How many years can they last doing different programs every night? Well, this is really just another way of saying how many possible programs are there. I guess you could say this is an application of the general product rule, because we have more than 2 components to our event. And so in this case, there'd be 9 times 27 times 15 possible events, or possible ways that you could play those 3 pieces, and that works out to 3,645, or about 10 years, conveniently. So the next problem we're going to look at is problem 35 from the textbook. And you can read the details in the text if you want. The basic story is that there's a company and they have different shift workers. In particular, there are 20 day shift workers, 15 who work the swing shift, and 10 who work the graveyard shift. And what the company wants to do is it wants to select a sample of any 6 workers and do some sort of a survey on them. And so this question concerns the number of ways that you can choose various combinations of workers. The key thing to realize here is that because we don't care the order in which the workers are interviewed, order does not matter. So the fact that order is unimportant means that we can use combinations to count the number of ways we can choose the event. So the first question, part A, is how many ways are there to choose all 6 from the day shift? And so that's just a straight application of the combinatorics, or the combinations. We just say that's 20. From 20 workers, we want to choose 6, which is 20 factorial over 14 factorial, 6 factorial. And when you do some simplification for that, well, we can do it in detail. It would be, well, you can simplify it. It's 38760 once the dust settles. The second part of part A asks, okay, what's the probability that all 6 are chosen from the day shift? In order to answer that, we have to figure out how many ways you can choose 6 workers, and that would simply be the total number of workers choose 6. So what we need to do is we need to find n of all 6 day over n. That is the number of ways we can choose all 6 day divided by the total, and n is going to be 45 choose 6. I say 45 here because we have 20 day, 15 swing, and 10 graveyard. So the total number of ways we could choose those 6 people from 45 would be that. So our answer is going to be 20 choose 6 divided by 45 choose 6, which works out to be our same 38,760 in the numerator, and the denominator works out to be over 8 million. And when we simplify that, we get 0.00476. So the chances are pretty small that all 6 workers come from the day shift, about 0.5%, give or take a little bit. And that makes sense, that you're unlikely to choose all 6 workers from less than half of the group. All right, so that's part A. Part B says, what is the chance that all 6 workers chosen come from the same shift? Well, this is a case where we have to break this down into a couple of different calculations. All 6 in the same shift, well, there's different ways that could happen. For example, they could all be in the day shift, they could all be in the swing shift, or they could all be in the graveyard shift. And those are mutually exclusive events, because if they're all day, they're not in any of the other shifts. So we can write that as the probability of all 6 day plus the probability of all 6 swing plus the probability of all 6 graveyard. Again, I'm adding those because they're disjoint events. We're interested in the probability of the union of those 3 things, but since they don't overlap, we can just add up the parts. And so now we can use principles similar to what we used in A. We already know the first part of this question. We know the first one is 20 choose 6 divided by 45 choose 6. That was our day workers. And then for the other workers, we know there are 15 swing shift workers. So it would be 15 choose 6 over 45 choose 6. And then for the graveyard shift workers, there's 10 of those. So we'd have 10 choose 6 over, again, 45 choose 6. And that works out to be, if you want to do the calculations, it's 43975 over our same denominator of 8145060, which is about 0.0054. It's reassuring to see that this number is slightly larger than the answer we got in A, since the event in B includes all of A and a little bit more. It's not much more, though, and I think that's probably because the 20 workers in the day shift are the biggest group. So it's even less likely that you choose everybody from the swing shift or everybody from the graveyard shift, because there's fewer of them. So there's part B. Part C says, what's the chance that I get at least 2 different shifts? There's a couple ways we could approach this. One way is to say that that's the opposite of they're all in the same shift, because they're either all in the same or they're from 2 or 3 different shifts. So we could say that's 1 minus the probability of all in the same shift. So I guess we're using the complement rule here. And we figured this out from part B. So that would be 1 minus 0.0054, which is 0.9946. Now part D is a little trickier. This one gave me some trouble initially to try and figure out. It's the probability that at least one shift is not represented. And in order to answer this question, what we're going to do is we're going to define several events, because it'll make the notation easier. So I'm going to say, let's suppose that the event A1 is the event that the day shift is not represented. And similarly, A2 will be the event that the swing shift isn't represented, and A3 will be that the graveyard shift is not represented. And by not represented, I mean there's nobody from that group. And you may recall from earlier in the question, there were 20, 15, and 10 people in each of those shifts. Now the event that we're after, the probability that at least one shift is not represented, can be written in terms of these events. At least one is not represented would be the union of those three, because the union means A1 is not, shift day is not represented, or swing is not represented, or grave is not represented, or more than that. So we want the probability of A1 union A2 union A3. And we can't just take calculate the probability of each of these and add them up, because there is overlap here. That is, you could have the day shift not be represented and the swing shift not be represented. That would correspond to everybody being from the graveyard shift. So we're going to have to use that general rule that we had for the probability of a union of three events. And it was this, that you add together the probability of each of the individual events first, and then we have to get rid of all those overlaps, so we have to subtract away the probability of all pairs, all intersections between pairs. So A1 and A2 minus the probability of A1 and A3 minus the probability of A2 and A3. And then finally we have to add in the probability of the intersection of all three, A1 and A2 and A3. So we got to figure out all these parts. And we'll do that one at a time. It's not as bad as it looks. So we want to figure out the probability of A1. And that's the probability that the day shift is not represented. So another way of saying that would be everybody comes from swing or graveyard. And we can do a calculation like that. There are 15 swings and 10 graveyards. So what we're saying is the number of ways we could choose that is going to be, there are 25 people not in swing shift, and we want to choose 6. And then we divide that by the total number of ways we can choose 6 people, which we wrote as 45 choose 6 earlier. And we'll just leave it like that for the time being. We could simplify this expression, but for the time being we're just going to leave it like that. We can use a similar idea for the probability of A2 and A3. Probability of A2, well, that would be nobody from the swing shift. So that's all day shift or graveyard. There's 30 of those people, so that would be 30 choose 6 over 45 choose 6. And similarly, the probability of the event A3 is going to be 35 choose 6 over 45 choose 6, because A3 is the graveyard shift is not represented, and that in turn means that we're not picking from that group of 10, we're picking from the remaining 35. So that's the first three terms here. We've got those three guys. Now we have to move on to the second row and figure out the probabilities of those intersections. So we're interested in the probability of A1 and A2. And A1 and A2 is that the day shift is not represented and the graveyard or the swing shift is not represented. So that means that's the probability that everybody is from the graveyard shift. And we figured that out before. Probability of everybody from the graveyard shift is 10 choose 6 over that same expression, 45 choose 6, the total number of ways. And similarly, we can get the other guys. So the probability of A2, now let's do A1 and A3. A1 and A3 is the probability of all swing. And all swing is 15 choose 6 divided by 45 choose 6. And finally, well, not finally, but the next one, A2 and A3 is the probability of all day. And we've written that one down several times already. It's 20 choose 6 divided by 45 choose 6. Now what we need to do is we need to figure out the probability of all three happening at once. That is, the probability that the day shift's not represented, and the swing shift's not represented, and the graveyard shift is not represented. Well, probably in the time it took me to write that out, you figured out that that's impossible. You can't have no representation from all three shifts because people have to come from somewhere. So this is the empty event. This is the null event. So we could write that as probability of phi, the null event, which therefore must be 0. So we're ready to put all these things together now. So the probability of A1 or A2 or A3 is going to be 25 choose 6 plus 30 choose 6 plus 35 choose 6 minus 10 choose 6 minus 15 choose 6 minus 20 choose 6 plus 0 all over 45 choose 6. And that works out to be 0.2885. This might be a good time to mention that you can do these calculations in R as well as on your calculator. So in R, to get 25 choose 6, type choose 25 comma 6. So you can use R to do these calculations if you'd like. All right, so that's a more complicated example involving combinations and some of the probability rules that we learned earlier. Let's look at another problem. This has to do with more with calculating combinations and permutations than actually doing probabilities. So this has two parts. How many different four-letter words can you form by choosing 4 letters from the word problem? And you don't have to worry about correct spelling. So in this case, it is important to remember that order matters because the way you spell a word includes how you what order the letters are in. But we're not going to worry whether it's actually a real word that you can find in the dictionary or not. So really, this is saying if order matters, how many ways can we choose 4 letters from a list of 8? And you'll notice that this problem, none of the letters are different. We have P, R, O, B, L, E, M. There's actually only 7, not 8. So we're looking at choosing 4 from 7. So we can use the product rule. Or, well, not the product rule. We can use permutations, I mean. And we would say, okay, there's for the first, well, it's going to be P47, which is going to be 7 factorial over 4 factorial, which is 7 times 6 times 5 times, I think I've got that wrong, because I want it to be 7 times 6 times 5 times 4. Yeah, I do have a mistake there. This shouldn't be 4. It should be 7 minus 4 factorial, which is going to be 3, and so that gives me 7654. If you prefer to just think of it as I have 7 choices and then 6 and then 5 and then 4, that's probably just as easy, in fact. So for the second question, we won't worry about simplifying that. The second question, part of the question says, how about from the word permute? How many ways can I choose 4-letter words from that? Well, this is a little bit trickier. We still have that order matters. However, we have to deal with the fact that there are 2 E's. And we're really interested in different words. How many different 4-letter words was part of the question. And so we've got to deal with the fact that there are 2 E's. So if I choose P-E-R-M, it doesn't matter whether I choose P the first E-R-M or P the second E-R-M. It's the same word. So we can't count those ones twice. So this is a little bit trickier. But we could break the problem down and say, okay, if we have words without 2 E's, then we could consider that we're really just picking them from P-E-R-M-U-T and forget about the last E. So for those words, it's as if we're choosing from P-E-R-M-U-T. That is, we have 6 letters to choose from, because if we know there aren't 2 E's, then it's like we're choosing from that. So for those, we would have 6 times 5 times 4 times 3 choices, or ways to choose those. But we also have to consider the case where there are 2 E's. Well, in that case, there's a lot of different places the E's could happen, but we could consider one of them. So if we have 4 letters, 1, 2, 3, 4, let's suppose for a minute that the first 2 letters are E's. Well, there's one choice for each of those, effectively, because we don't care about the ordering of the 2 of them. But then for the remaining 2 letters, we have 5 letters left that we could choose from. So there's 5 choices for that letter, and then 4 for this. So there's 20 ways we could choose a 4-letter word beginning with 2 E's. But of course, there's more than that many. There's different ways we could arrange the E's, and every time we arrange them in a different way, we'd have 20 new ways. So what we could do is we could think about how many ways can we arrange 2 E's in a list of 4. Well, we've done one of them already, E, E, and something else. We could have the E first and have the E here, or we could have the E first and have the other E last. Those are the only ways we can put the E, the only ways that we can put the E at the beginning. So then the other choices would be E in the middle. We could have it like this, or we could have E, nothing, E, or then finally, if we don't have the E in the first 2 locations, it has to be at the end, and that's it. There's only 6 ways. Incidentally, you could use combinations to choose this, because you could think of this in terms of combinations as I have 4 locations and I'm choosing 2 of them to place the E's. So you could say 4 choose 2. That is 4 locations and 2 places we put an E. Now, if that's not easy, you can always, in a case like this, just list them as well. Either way is fine. So putting this all together, we have 6 times 5 times 4 times 3 ways to choose a word with either 0 or 1 e's in it. And then the 2 e's, we have 20 times 6. And if you add that all up, you get 480. Now, I must confess that when I did this, I wondered whether I had it right or not. It's a little bit of a tricky question. So this might be a good point to mention that in some cases you can actually check your work using R. So get it to do the calculations. And this is somewhat advanced R programming. So I'm not going to expect you to do this on an assignment anytime soon, but I do want to get you used to the idea that you can use R to do a lot of these calculations that we're doing by hand on paper, and it's a handy way to check your work sometimes. So let me just explain the code that I'm using here to do this. So I made a variable called permute, and it was a vector with the letters P-E-R-M-U-T-E in it. And then what I'm going to do is simply tell R to do this sampling many times. So just randomly pick 4 from the 8, and then I'll count how many unique words I get. So this is just setting up an empty matrix full of A's, and it has 10,000 rows and 4 columns. And then I'm going to loop over the number of rows in this words matrix, which is 10,000. So I could have just written 10,000 here also. And in that loop, I'm going to every row of that matrix, I'm going to sample 4 elements from the vector permute. So I'm telling R, randomly pick 4 letters from this list of 7 and save them in that row of the matrix. So here's the first 5 I get. And just by chance, the first sampling it actually did choose P-E-R-M, the first 4 letters. But that was just a fluke. You can see these are in this case, the first 5 are different. It's quite likely that some of them are going to be the same. In fact, it's, I guess, a guarantee since we asked it to choose 10,000, and we think there are 480. So what I've done is now I've asked R to tell me how many unique combinations there are. And there's a handy command in R called unique that will just filter out everything every row that's a duplicate. So this is basically making a new matrix which has as many rows as there are unique words that it found. And when I count how many rows, it tells me there were 480. Now you may be thinking, well, what if it didn't sample all of those? And that's possible. But you'll notice I made the number of samples it drew 100,000 actually, not 10,000. I better correct that. 100,000. I chose 100,000 samples, and so it was fairly likely that it would hit all 480 at least once. And so it gave us the right answer, and we're now pretty confident that we have the right answer. So I think what I'm going to do now is I'm going to stop the lecture here because I've covered about all I need to cover. I might be a few minutes short, but I think it'll take you a few minutes extra to get YouTube up and running and so on. I'd be very interested in feedback on how this worked because I may be away once or twice later during the term, and I'll be interested to know how it works. Thanks, and see you on Monday.